ad infinitum. In asymptotes, x equals 1 at vertical asymptote. Done deal. So now to the back page. Let's flip it over. Let's talk about evaluating these logs, and I'll just walk through them all kind of quickly. Again, just pause and take a deep breath. Play it again if you need to. The way you want to evaluate these logs, I prefer to, is I think 1/4 to what power is 64. And when I figure that out, that's going to be the value of this thing. And so here it is, 1/4 to what power is going to be 64. And you may not know. So if that's something you don't know, put a y in that spot there. Make 1/4 to what power, give it a variable. I like y, it's easier to work with. Equals 64. I think, oh, I still don't know, I haven't a clue. The next option you have is to try and write each one of those in the power of something that you're more familiar with. Like, I don't know, what are powers of 4 that you know? So if you think of 64, what are things you can do with that to the 4th root or something like that? So if I were to think carefully, what is that? I could do squareds. Just 2 times 2 is 4, times 2 is 8, times 8. Hey, wait, 8 squared is 64. So those are things you start coming up with as you go along here. This is 2 to the negative 2 is a good way to do 1/4. Sorry, I was actually doing a text at the same time. I got a little sidetracked there. And then 64, if you do some kind of power, like 2 to the 3rd is 8, 2 to the 4th is 16, 2 to the 5th is 32, so 2 to the 6th is 64. Once you get those side by side in terms of base 2, the same base, that's when you can compare the two exponents. But the goal is, if you can't figure it out after changing it to exponential form, which is what this is, converting to exponential form, keep that in mind, that's an important process. When that exponent relationship isn't clear, try and write them in terms of the same base, like 3 to some power, 2 to some power, 5 to some power. Those are pretty common ones. Now that I'm here, I can say, hey, negative 2 times something is 6, if these are equal. Or if you don't know how to solve it, just talking it through, negative 2y equals 6. Set the exponents equal. Divide both sides by negative 2, and you get negative 3. And that ends up being the value of our particular log. Log 1/4 of 64 is negative 3. Some of the other ones are easy. 9 to what power is equal to 3, and that's a square root. So that's a 1/2 power. 9 to the 1/2 power is 3. 2 to what power is negative 8? You can never input negatives into a log, so this one does not exist, undefined. Can't input. You can have negative output. So here's the contrast is, can't put a negative number. That's undefined. But you can have a natural log of some number, and it can be a negative number, and that's okay. Okay, you can have a negative output, but you can't input a negative number into a log. And the way you see it in the graph, it manifests itself as, when you look at a log graph, there are no negative numbers that you can put into a log, so the input can't be. But you'll notice that the log can get very negative indeed on the right side of the graph. Last one. Be careful with this one. A couple ways to think of it. 4 to what power is equal to 4 to the 2x, and it's just 2x. 4 to the 2x power is equal to 4 to the 2x. Sometimes it's helpful to think of it as log base 4 of 4 cancels, and that leaves behind just 2x as well. Also a nice way to think about it. Moving on, we got to expand these. When you count, when you're doing logs, it's how many logs will I have when I expand it, and you're going to have 2. You're going to have the x in one of them, and you're going to have the 10 in the other. You know that to be true, and then you have a log for each one of them. The only thing that might be of interest to this one before we do that is you do want to make that 5th root into a 1/5 power. So I'm going to switch it to being 1/5 up here. Now, I'm happy to go either way. You can pull that 1/5 out right out of the game, right out of the chute, or you can just distribute it amongst what's in here. I'm going to pull it out front to begin with because I think in a lot of situations it's a little cleaner. And what that means is when I get done, all I'm going to have is, I'm going to remember that when I'm done, multiply everything by 1/5. Because the thing I'm going to expand is ln of x over 10. You'll see that in my brackets. Oops, right over here, to leave room. Okay, ln of x over 10. If I block this off, this stuff in the box there is just me expanding the ln of x over 10. So you do an ln of x, and you do an ln of 10, and then because there's a division between those two, you subtract. Done. Okay, so that's one way to tackle it. Next one, how many logs do we get in the end? 1, 2, 3, 4. So make sure you get yourself room and just go log base 2, log base 2, log base 2, and log base 2. And a 4 goes in one of them, and x squared goes in the other. A square root of y goes in the other. I'm being pretty straightforward this time. I'll fix it in a minute. And anything that's in the numerator, you add those logs together. Anything in the denominator, you subtract those logs. Final step is, are there any powers? Half square root counts as a power that you need to pull out front. Take care of those. And any simple logs like log base 2 of 4, 2 to what power is 4? That's totally just 2. So you can evaluate those. Take care of those easy logs, pull powers out front, and you're done. Got those. And don't remember, square root is a half power, so we want to put the half out front. Log base 2 of y, and then minus log base 2 of z, and we are done. Okay, expanded. Finalmente, we get to this last one. 27 x to the 5th y and square root of z. That's 1, 2, 3, 4 logs again, and just follow that same process. Log base 3. I'm going to work a little bit more directly. I know 27 goes in 1, and then those are on the top, so I'm going to add it. Log base x to the 5th, or I'm sorry, log base 3 of x to the 5th. But instead of putting it to the 5th power, I'm going to bring it out front from the start. You can see my emails coming in. And then plus log base 3 of y. I'm going to run out of room, so I got to go down a notch and then subtract what's in the denominator, log base 3 of the square root of z, but no, I'm going to put z here, and instead of the half power, I'm actually going to pull the half out front from the beginning. So that would be almost done, and I did some of the exponents right as I was expanding it. But I would want you to take this log base 3 of 27. Since it's 3 to what power is 27, that would be 3 to the 3rd, and go that extra step. Okay, so make that into 3. You can even put an arrow and tuck it in like that. Okay? Sorry it's fast again. I know. Pause and rewind as needed. I know I'm moving quickly. Here we are condensing logs. To condense logs means when you're done, you're going to have a single log. Do not write the log repeatedly at any time. It's just one log, since they're all the same base 10, even though it's not written. Anything added goes in the numerator, anything subtracted goes in the denominator. You want to move any powers that are out front of those logs back up top first. So this is x to the 3rd. This is y squared when you get that back up top, and you can move them out of there. Then when you put it back together, then it's x cubed on top, x plus 1 on top as well, and in the denominator we have a y squared from moving those powers up there. Done. No other simplifying is necessary. I'm interested in the log rules, not algebraic simplification stuff at this point. So let's keep it simple. I see 2 logs, but we're going to condense it to 1. And I'm going to make my little fraction bar because I see a minus sign in there. Power's up top first, so I put that 1/2 up there. This goes on top because it's a positive log. X minus 2 to the 1/2. And the one that's subtracted is, I'm putting the 3 back up to the power. So it's actually 3 to the 3rd. And that means on the bottom I'll have 3 to the 3rd, which is 27. You could leave it like this, but just for fun, this is perfectly okay, by the way. You could do the square root of x minus 2 over 27. And that'd be extra, extra cool, but not necessary. All right, on we go. Last things is evaluating using a calculator. You can do this with calculators math. If you go down to the A option, there's a place to do logs of different bases. But if you have one of the older calculators, it's actually good to know the change of base formula that happens in number 17. You can rewrite any log that you see, log of any base, as the quotient of 2 logs of, like you pick a log that you like, natural log. You can do a quotient of ln of 8 over ln of 5. That's equivalent to log base 5 of 8. You could choose log of 8 over 5. That's fine. You can choose any base you want. And so sometimes I write log of base A, which is unknown, anything you want it to be, over log of base A, as long as it matches the one above. That is a way of rewriting the existing log in terms of a different base. Okay, so that's the base change formula. It's used for older calculators. That's how we did these logs. So for instance, log base 5 is 16. If I didn't have the log button in my calculator, I did ln 16 over ln 5, hit enter, done. Okay, last one here, if you have an old calculator, then you got to put in ln 7.5 over ln 1/3. I'll let you get those with your calculator. And of course, this would just be straight up into the button. And last one here, cannot take the log of a negative number, so you get error, which just means it does not exist. Okay. To the solving, because this is where we earn the big bucks, and then that'll be the end of this little video. I think I'll do these two basic ones, 5 and 6, and then I'll hit stop, and then I'll go and do the rest in another video. Okay. When you do logs, or solving, I should say in general, your job is to isolate either an exponential function or isolate a log function. That's what I'm going for. So you isolate the function of choice, log or exponential. And then you apply the inverse. That's, if it's a log function, you do the exponential conversion, or I do what's called exponentiating. If it's an exponential function, you take the log of both sides to undo the exponent function. That's the inverse operation. So you apply the inverse of your choice, whatever fits the type. Sometimes this happens multiple times within a problem, but you'll see it when it comes. For instance, hey, I can see the log there. I'm going to get it by itself. I'm going to isolate it. Things I need to do are like, hey, get rid of that 2. Divide by 2. Divide by 2. This is not the only way to attack it, by the way. Some of you are thinking, can I put the 2 up here in the exponent? Yes, but let me just try one route first, and then if you want to come back to another, you can let me know. So now I've got log base 7 of x minus 3 is equal to 2. This is the point where I would undo this by converting to the exponent form. So 7 to the second power equals x minus 3. 7 squared equals x minus 3. 7 squared is 49. And if I add 3 to that, 49 plus 3 is 52. Got it. That's our result. X is 52. The thing I was mentioning before, this verb exponentiate, I'm going to show you now. Let's see what you think of it. I could have, so what we'll do is we'll call this a little like kind of separate trip we'll take over here. I could have raised both sides, to the 7 power. 7 raised to the power of log 7x minus 3, and 7 raised to the second power. It's kind of the verb exponentiating. I am actually purposefully using the inverse operation to get a cancellation to occur. Because what I will notice now is, if you remember in some of our work before, 7 to the log 7 power cancels. And so this takes me over toward, remember they cancel, like the log 7 and 7 completely annihilate each other. X minus 3 is left on the left-hand side, and 7 squared is all that it remains on the right-hand side. Do you notice we're in the same place we just were a minute ago, and I can solve x equals 52. Same idea. This is the process I call exponentiating. Yeah, 7 up both sides there because it's a log base 7, and that cancels it. All right, one more and then I'll give you some more examples in a minute. Let's go back to the old red color. This, I need to isolate the log, so that means things like subtract 8, subtract 8. Get those things alone. And then I have negative 3 ln x equals 4. Divide by negative 3, divide by negative 3. Get rid of things that are attached to the log. Okay, and then at this point, you might not know what to do, but it's, well, I forgot the x in there. There is a base e in a natural log function. If you want to do what's called the conversion process, you go e, get a different color here. You go e to the negative 4/3 equals x, and that'd be just fine. E to the negative 4/3 equals x, and you'd be done, by the way. That's actually done. You have x by itself, and you can move on. The other option you have is to do that exponentiating thing I was talking about. So imagine I was just looking at this a minute ago, clean and tidy, and I just e it up on both sides. I exponentiate both sides. E to the power of ln x, e to the power of negative 4/3. E and ln cancel. X equals e to the negative 4/3. That process of exponentiating gets you the same result, and it has kind of a nice cathartic, sensical feel to it. So I highly encourage it. All right, that's video 2.